Yesterday, we looked at an even function, the definition of an even function, that f of negative x is equal to f of x. And then we talked about what that means in terms of the graph of an even function. So if f of negative x is equal to f of x, then the graph will be symmetric about the y-axis. That is, the left side of the graph will be a mirror image of the right side of the graph. And here we can see why. If we have x and its opposite negative x, we get the same value. So that's what it means to be an even function. In terms of the definite integral, we're interested in things like the area under the graph and above an interval. So we would be interested in this area in here and this area in here. So what we notice is that if the left side looks the same as the right side, and this x is the same distance from the origin as this negative x is the same distance from the origin as this x, then those two areas must be equal. So these two areas must be equal. So what that means is that if we're integrating an even function, let's say from negative a to a, we're just going to get two copies of the integral from 0 to a. So this will be 2 times the integral from 0 to a of f of x dx. So this multiplied by 2. So that's what we get when we learn that f of x is an even function. So let's apply this to what we are given. We are given, in the problem, it says, if the integral from negative 4 to 4 of f of x to x, of f of x minus 4 dx is equal to 4, then we want to find the integral from 0 to 4 of f of x dx. So here we're just going to use properties of integrals. I have the integral from negative 4 to 4 of f of x minus 4. I have two terms. And since we know that differentiation and integration are linear operators, I could just split this up. So this part, this integral can be rewritten.
I have a question. Why does it say minus 4 after fx?
That's just part of the problem.
Oh, okay.
So I can split this up into two integrals. So we can integrate from negative 4 to 4 of f of x dx minus the integral from negative 4 to 4 of 4 dx. So now we can use the fact that f of x is even and rewrite this integral. So since f of x is even, I can write the integral from negative 4 to 4 of f of x dx as 2 times the integral from negative 4 to 4. Oops, sorry. Replacing this negative 4 down here. That's the whole reason I wanted to do this. 2 times the integral from 0 to 4 of f of x dx. We still have to subtract the integral from negative 4 to 4 of 4 dx. And all this is still equal to 4. Now all we have to do is solve for the integral from 0 to 4 of f of x dx. We can calculate the integral from negative 4 to 4 of 4 dx. Then we'll add that to both sides and divide by 2. So now that we've rewritten the the given equation in terms of the thing that we're looking for, we can just solve for the thing that we're looking for. Integrating from -4 to 4 of 4 dx, we can do a couple of different ways. We can use the fundamental theorem of calculus, or we can use geometry. So with the fundamental theorem of calculus, we would say this integral using the fundamental theorem of calculus, this integral from -4 to 4 of 4 dx. The fundamental theorem of calculus says find an antiderivative of the function and evaluate from -4 to 4. So we would plug in the 4, plug in the -4, and simplify. So this will give us what, 32? We can also use geometry. If we think about what this graph looks like, so I'm going to go up here and evaluate it with geometry. If we think about what this graph looks like, or what we're looking for in this definite integral, we're looking at the function y equals 4, and we want the area from -4 to 4. So that area is equal to 32. So both ways give us this integral from -4 to 4 of 4 dx, a value of 32. So 2 times the things we're looking for, minus 32 is equal to 4. So the thing that we're looking for is 18. Any questions?
Yeah, where does the 4 dx come from?
The 4 dx is this term right here. So I took this integral, f of x, the integral of f of x minus 4, and I just broke apart the terms. There's the first term, there's the second term. So I split off this first term, integral there, and this second term is right there. Any other questions? All right.
Professor, I was trying to find the mute button. Are you saying that function is, or that integral is even because it's 4 or because of something else?
The integral is not even. Integrals aren't even or odd. The function is even. We're given that f of x is even in this problem. So that applies just to the function.
I understand. Thank you.
Any other questions? All right. Another mute button is the space bar. So that's another option. If you're used to push to talk systems, if you're on mute and you want to come off mute just temporarily, if you hold the space bar, that'll unmute you.
Good to know. Thank you.
Yeah, that way you don't have to click around for menus.
Much appreciated.
I don't know how y'all like to navigate programs, but if there's a keyboard shortcut, I want the keyboard shortcut. If I have to click in through a menu, I'm very angry at the person who put the UI together. I'm like, oh, come on, man. Clicking on things. I know some of you are like all big fans, are going to be big fans of the drop-down menu, but no. If I have a keyboard in front of me, I want keyboard shortcuts. So future computer people, leave off keyboard shortcuts if you want to make me angry. You know what I'm talking about? I'm looking at you, Roll20.
When it says f of x is even, can we just think of that as being that it's an even power, that it's x to the second, x to the fourth, x to the sixth?
That's the best way to think about an even function. And if it's a polynomial, all the powers will be even. But things like cosine x is also an even function. So there are even functions other than just polynomials. But if you need an example of an even function, x squared, x to the fourth, x to the sixth, perfect. Any other questions? All right.
I just had a question.
Yeah.
Finding the antiderivative of the constant is the constant times the variable plus c.
Yes.
Okay, so I'm just make sure.
Yeah, so we're thinking what has a derivative of just 4? The derivative of 4x plus some constant is equal to 4. We don't need to write the plus c because we're doing a definite integral. And we'll have a plus c in when we plug in 4. Then we'll have a plus c when we plug in -4, and then we subtract them. So the plus c's will cancel out. So when you're evaluating a definite integral, just find any antiderivative. And the most convenient one is where that constant is equal to 0.
Okay, thanks.
All right, so on question 5, let's talk about question 5. In this case, I'm looking at you, Wiley. So I don't really have a problem with subsequent parts of this problem, but I do have a problem with the first part. So this is 0, 2, 3 times 2. So in 5, let's see, chapter 5, section 4, problem 5. We're given a graph. And then the first thing I see is that we're evaluating an integral from -3 to 3. And I see that the graph is like nice and curvy. They don't tell us what the function is. And it goes through some weird points. It doesn't really go through very good points anywhere. Which means asking you to evaluate it is kind of unfair, especially because it's like plus or minus 2%. So we have this function. I'm gonna try to draw it here. I probably shouldn't be undermining the book so hard, but you know, I started doing it last semester. I have to blame someone for my failures. So it looks like we've got this part here. And we're doing a definite integral, so I'm going to be caring about things like where this is above the x-axis and where it's below the x-axis. And we're just going to have this part down here. So this is a reasonable approximation of what we're trying to look at. It also looks like these zeros of this function happen at -3, which is relevant to our interests. It looks like this one to me happens at 1. And it looks like to me this one happens at about 3.5. And so what we're actually interested in, so there's a little bit left off between 3 and 3.5. Now I exaggerated this only a little bit. If we look at the two areas, if we think about the two areas that bounded by this function, the graph of this function and the x-axis, we've got this big negative area and this smaller positive area. Let's call the smaller positive area A2, and we have a bigger negative area. let's say that that bigger negative area has an area of A1. So what I mean is that the definite integral from -3 to 1 of this function, oh, it does have a name. This function is like, well, I have a name, you know. So the definite integral from -3 to 1 will be -A1. I list area as being a positive number, but the definite integral will calculate area below the x-axis as a negative number. So the integral from -3 to 1 of f of x dx will be negative whatever that area is. And the integral from 1 to 3 of f of x dx, now we're above the x-axis. That'll be whatever our positive area is. So if we combine these two together, the integral from -3 to 3 of f of x dx is, we'll have some negative area, so -A1. And this process is additive, so we'll just add A2. We'll also observe that since it looks like that A1 is a bigger area than A2, that means that the antiderivative decreased more than it increased. So we expect this to be negative. So we would also observe that since A1 is bigger than A2, this definite integral will be negative. Somehow, based on these calculations, you are supposed to determine that the integral from -3 to 3 is equal to -4. I tried a couple of times to get a -4 and I didn't, so I'm not sure what their I just haven't landed on the correct set of approximations. So if you happen to come up with -4 for some reason, let us know how that works. Nice number if you can get it. And if you get it, won't you
I
tell us
think
how?
from 3 to 1 is supposed to be 6, and the other one is supposed to be 2. But I have no, that was my question. I understood this part, but how they came up with their friggin' numbers, I have no idea.
Yeah, so that certainly, it seems perfectly reasonable. That would result in a -4, but I just didn't get the same numbers that they did. When I tried to do a delta x of 1, and then when I tried to just separate it into different things. So anyway, more important, if we look at the following average values of f of x, if we think about averages, averages are where we add everything up and then divide by the number of things that are there. So if we look at the average value of a function, the average value of a function f of x on the interval from a to b, what we do is the same thing that we do when we're finding the average of a discrete number set. We add up all the values and divide by how much is there. We do the same thing with a continuous sum. We add up all the values in an integral and then divide by how much is there. So just when you're comparing the two average values, between 0 and 3, we'd integrate. So the average value on the interval from 0 to 3, we'd have 1 over 3 minus 0 times the integral from 0 to 3 of f of x dx. Yeah, 0 to 3.
Don't we want to use 3.5? Or did they tell us to use 3?
No, this is which of the following average values is bigger, and it's between 0 and 3, or between -3 and 3.
Oh, okay, got it.
And then the average value on the interval from -3 to 3. So whether we actually get these values or not is, I guess we do kind of need these. No, we don't. What we notice is that if we look at the graph from 0 to 3, it's mostly positive. It looks like it's pretty positive because the integral from 1 to 3, that looks like more area than from 0 to 3. So it looks like this is going to be positive, and then we take that positive number and divide it by 3. But if we look at the integral from -3 to 3, that is definitely negative. So this number is negative. And but the integral from 0 to 3 is possibly positive. So the bigger one is the positive one. We don't actually need these values since the second one is definitely negative and the first one is positive. The positive one, whatever number it is bigger than the negative one.
So then how does this relate to what we were just talking about, like even functions?
It doesn't. We left behind, this is not an even function. So we're not using that in this problem.
Oh, gotcha. Okay.
Any other questions? All right, the other question. All right, so on the other one, so we want to find the area of the region between -x² plus 6x minus 5 and the x-axis for x between 0 and 4. All right, and we have a picture of what's going on here. So we've got a parabola, and it looks like we have zeros at 1 and 5 and a y-intercept of -5. So got an idea about what this graph looks like. So we're going to draw a parabola. And this is the graph of y equals -x² plus 6x minus 5. So we know where some of these points are. It doesn't matter, but we should always, if we know some points, identify what those points are, because that's useful. So this is going to happen at 1. This is going to happen at 5. It's not going to be relevant. So we've got this axis of symmetry. That'll be halfway between the intercepts. So that'll happen at x equals 5 and 1 is 6 divided by 2 is 3. But we're actually going up to 4. So what we want, this is up to 4. That's part of the problem. So the -5, the 1, and the 5, and the 3, those are all things we get just by observing about this parabola. What we're actually interested in is we've got some negative area in here. And some positive area. And this one says find the area. So what we're going to do is we're going to separate it into 2 parts. the definite integral is going to report that red area as negative. So we're going to make it positive. So the definite integral will report the integral from 0 to 1 of f of x dx as negative. So we're going to have to take the absolute value of that to find the area. Otherwise, that negative area will cancel out some of the positive area. So the total area that we want, we're going to integrate separately from 0 to 1 of f of x dx. And then we're going to change the sign because it's negative. And then we're going to add the integral from 1 to 4 of f of x dx, which we'll keep because that area will be, the definite integral, we'll call that positive. So we have to change the sign of this area. If we take the absolute value of the function from 0 to 1, that will give us positive area. So we want positive area and then the opposite of the negative area. So absolute value, because we want area, not the change in the function. And this we can calculate with the fundamental theorem of calculus, or since they're asking us to round the answer to 3 decimal places, that tells us to skip the fundamental theorem of calculus and just use the calculator. So we can use the fundamental theorem of calculus, or use the calculator, since we're rounding anyway. We can either use the fundamental theorem of calculus, or we can use a calculator since we're rounding anyway. Fundamental theorem of calculus would be for things like the exact value. But as soon as you see in a problem, round your answer to 3 decimal places, that's when calculator should make an appearance. It's going to come in at an angle like this, like, oh, did someone call for a calculator? And so we'll just math. And if you scroll down, number 9 in the math menu, it's going to smear, oh well. Number 9 in the math menu will bring up a numeric integral. And we want to integrate negative x squared plus 6x minus 5 with respect to x from 0 to 1. As suspected, this gave us an why did I come out positive? Did I miss something? Oh, because I put plus 6. All right, there we go. So as suspected, this comes out to a negative 2 1/3. And then if we do this separately from 1, there we go, to 4, we got 9 for the rest of the way. So the total area is 11 1/3. But the integral from 0 to 4 will be 6 2/3. So notice a relationship. If we integrate all the way from 0 to 4, that'll subtract those 2 values. But we want the area bounded by these boundaries. So we should make the negative area positive. That's why we had to integrate in 2 different integrals.
So just for my edification, if it asks for area, excuse me, then we want to add them together, whether it's negative or positive, and make it positive for total area. But if it just has the integral signal, shh, sorry, 2-year-old.
Okay.
And then if it just has the integral symbol, then you know, combine it.
Then
And
you can do it all in one
subtract it.
integral.
Yeah.
Correct.
Okay.
So yeah, if you want the total area, you have to break it up into negative, the parts that'll be negative and the parts that'll be positive, so that you don't get cancellation.
Are you not a fan of math print? Just out of curiosity.
I'm not, because when you do the when you type it in single line syntax, that's the sequence of buttons you have to press anyway, and I just prefer when you're communicating with a computer to type in single line syntax.
Okay.
Plus, I mean, it gives you a way. Let's suppose that you're communicating with your friend via text message to work on some problems. I can't do math print on this machine. So,
Got it.
any other questions? Great. All right, that takes us to the end of the chapter 5 homework. So let's talk about what's coming up next. Just introduction to what's coming up next. Oh, I labeled this as page 1, so I'm gonna have to go old school. There, now it's page 2. This was page 2, right? Oh, no, it's page 3. There, now we're old school. I seriously don't understand how the Romans got anything done with their terrible numbers. I guess running an empire back then was really more about just like beating people up and taking their stuff. So
There's a reason
They
they're
didn't
not
need
the
to
world
add stuff.
power anymore.
it was those dumbass numbers they were using. All right.
I like to blame Saturnalia.
Let's talk about, I could come up with reasons, but then again, the history department might be like, call me up. It's like, hey, Leach, stay in your lane, man. I go, no. Y'all spread lies about the math department. I'm gonna spread lies about your history department. And by the way, if I started lying about like history and stuff like that, that's an American tradition. So, I mean, yeehaw. What are we talking about? Oh yes, what's next? All right. It's worse because I was in school in like 70s and 80s. So I was getting the super patriotic, go USA version of American history. So if you're in your 40s or your 50s and all you can think of, and you only have negative associations with the Soviet Union, you got to think there's a reason for that. You were raised to be that way. And you might not have access to the actual truth. Just be aware of that. Not saying it was the opposite is true. I'm just saying be aware that the things that you believe are not, have been, you were taught propaganda. I guess that's what I was saying.
Conditioned.
Yes. Let's talk about what's coming up next. What's coming up next is the other side of the fundamental theorem of calculus. The other part of the fundamental theorem of calculus. The other part of the fundamental theorem of calculus, we've only got a few minutes, so I'm just going to introduce this topic and say it's in chapter 6 and then be like, oh, bye. So, which is, if you've been in my class before, is something that you should be used to. It's like, oh, hey, here's almost no introduction to the next homework assignment. Now go do the next homework assignment. And then the students are like, oh, but, end meeting for all. So that's just how it works. Let's talk about the other part of the fundamental theorem of calculus. The other part of the fundamental theorem of calculus is about constructing antiderivatives. That's the big deal that we get out of this, constructing antiderivatives. This is a big deal. So let's just state it and then talk about why it's significant. So let's let f of x, oh, I spelled let wrong. Yikes. Let f of x be continuous on a closed interval from a to b. And we also need any value from a to b. So let's let c be some real number between a and b. Then. So I got a continuous function on a closed interval and some value from that interval. Here's the actual statement, the claim that we are making. The integral from c to x of f of t dt, oops, is an antiderivative of little f of x. It's usually called capital F at x. I'm not sure I'm a big fan of this, use the capital to denote the antiderivative, but the important part is that if we define capital F to be this function, the definite integral from any point to x of f of t dt, we will get an antiderivative of f of x. So what we are doing is constructing an antiderivative using the definite integral. That's the big deal here.
Why does it
We can
switch to t from x?
Because I want to plug in x, I want a variable in the end, and we end up in kind of a being John Malkovich situation if I have the integral from c to x of f of x dx, because I'm plugging x into x. So we institute this dummy variable. We find the antiderivative with respect to t, then we can plug in the x wherever the t is. So it's kind of a formality. That's not the sneaky part.
Professor, what's that CE next to AB? Is that, sorry, I didn't catch.
C is an element of. So this is the symbol for is an element of.
Okay, thank you.
So what we're doing here is we're constructing an antiderivative of a continuous function using the definite integral. Construct an antiderivative of a continuous function using the definite integral. So if you're writing this down, make sure you put an exclamation point at the end of that, because that's the big deal part. We're constructing an antiderivative using the definite integral. The reason that this is a big deal is that we can approximate definite integrals with area. So all we need to construct an antiderivative is length times width. So this part is the big deal. All we need is area. That is the dope part of this second part of the fundamental theorem of calculus. It allows us to construct an antiderivative using the definite integral. Since the definite integral can just be approximated with area, all we need to construct an antiderivative is area. All right, then all we actually need to do as students of calculus is to figure out what this has, how this is going to show up in problems. Because right now, when you're a student in calculus, you're not concerned with big ideas. You're concerned with solving problems, specifically the problems that show up on the homework and any quizzes. But as the teacher of the calculus class, I care about the big ideas and the way you think about things. This is why teachers and students don't really get along all that much, because they have different goals. My goal is for you to learn calculus. Your goal is to get an A in this class. I know you think those are the same thing, but I assure you they are not. Anyway, this is where we're going to leave it today. Go back and review the homework from chapter 5. So we have that in our pocket moving forward. Then start looking at the problems from chapter 6. Any questions?
Do we have due dates for chapter 6 or not yet?
We don't have due dates for chapter 6. We're not sure when we're going to be done with chapter 6 yet. So the due dates for chapter 6 will be forthcoming. The other big thing that we want to be able to do is to start finding antiderivatives. So here we can construct antiderivatives. So the process of finding antiderivatives is not super necessary, but we're going to do it anyway because it's good training. It's still a good skill to have. It's not that you're going to be working for SpaceX, sending missions to Mars and finding antiderivatives by hand. If you're working for SpaceX and you're about to find an antiderivative by hand, you're probably about to get fired. So that's not the point. If you want training for some job, don't go to school that has no idea what jobs are. Go get the job and find out what they need you to know. So if you come across, and if you're working in industry as an engineer, if you come across a math problem, you're probably just going to hire a mathematician to do it anyway. But it's going to be really embarrassing if you don't know how to do integration by parts. I don't know what happens at like engineer parties. I think they hang around and do integrals by hand. It's like, oh, let's do some trig sub. And they're like, oh, woo. I don't know. I got kicked out of the school that had fraternity, so I don't know what the hell goes on in those places. All right, that's going to do it for today. Review your chapter 5 homework. Start working on the chapter 6 homework, even though I've almost talked nothing about it. And I will see you all on tomorrow. That's it for today. This will be up on the YouTubes, so don't forget to smash that like button. Actually, you don't have to hit the like button.
Professor?
Yes.
Yeah, I saw the YouTube video. Those you already cut down the you already edited, right? The YouTube.
I don't edit them. I just take the video and I just stick it up on YouTube.
Oh, okay.
So.
All right.
All right. That's going to do it for today. I will see y'all on tomorrow, and thanks for playing.
Thank you.